Is it up there? Okay, let's get started. So I posted your homework for Wednesday. Posted that yesterday. Get started soon. Okay. We're talking about exponential functions, and we're kind of seeing in the last couple class periods there's the centerpiece to all exponential functions. It's the most everything comes out of this one thing. What did we say that was? Exponential functions are based on this one principle, this one value. The growth factor. Yep. Repeated multiplication. But the value is the growth factor. Okay, that's kind of, when you say growth factor, that's kind of generic. It can mean either growth or decay. But it's when you have decay, it's better to call it decay, just so there's no confusion. But kind of growth factor sometimes is just used generically to mean a growth or a decay factor. And what is the growth factor? Someone said over here. It's the number that you keep multiplying by. It's this number you keep multiplying by. Okay, so is the multiplier, is it a number that you multiply? So there's input and there's output, okay, of the function. What do you multiply the growth factor by, and what does it give you? Do you multiply it by the input and it gives you output? Do you multiply it by the output and it gives you input? Do you multiply it by input and it gives you another input? Or do you multiply it by output and it gives you another output? So talk to the person next to you. What do you multiply it by, and what does it give you in terms of an input-output of a function? Go.
I'd like to find out someone who's paying attention. Would it be input?
Oh. Oh, my computer is not happy. She's breaking up. Yeah, it's not liking something's not happy. Okay, sorry, my computer is not happy. Let's try it again here. What am I doing? Not that. Okay, that's better. Okay, cross our fingers here. Let's hope it works. Oh, there we go. See the bomb? Crash and burn. It means this, my pen writer is crashed. So let's see if we can. Trying to quit out of it here. Let's see if this works. Okay, while I'm experienced technical, just let's get started. This will be going to be later in class. Why don't you work on page 145? Work on page 145. Okay, I think we're back.
Return page holder changes.
There we go. Oh, come on.
Corey, for number 1, for A, it's flawed. Because it's asking for 14 minutes after the first observation, which is 100.
Well, after 7 minutes, it's 100. So 7 more minutes, it's going to double from 100
Yeah,
to
to
200.
200. But then it says that is 14 minutes after the first observation. Isn't the first observation 100?
The biology observes an IV features there are 50 micrograms after 7 minutes.
Okay, I'm back online. So put that on hold for a second. So we said the growth factor. It's the number we keep multiplying by. The question is what? So if we have this function, do we multiply the growth factor by input, or do we multiply it by an output? And then what does it give us? Does it give us an input, or does it give us an output? So I demonstrated k of 2. What would k of 2 be? It'd be 12 times how many 1.28s multiplied together? 2. K of 3 would be 12 times 3 1.28s. Okay? So compare those two outputs, and you tell me, what do you multiply 1.28 by? Input or output? And what does it give you? Input or output? So look at my example there, and talk to your person next to you for about 30 seconds. See what you think. Okay, let's hear what you think. First of all, does it make sense to multiply the growth factor times the input or times the output? He says output. Input. What do you think?
Because your inputs are 2 and 3.
Okay, so here's the input 2. Did we multiply 1.28 times 2? Is that what we did? No, we never. Where did we multiply 1.28 times 2? 2 is what? It's the number of times that we multiplied 1.28 together. So really, did we ever multiply 1.28 times 3? No. What did we multiply 1.28 times? If you take the output from 2 and do what? Multiply it by another 1.28, you get the output of 3. So it's a multiplier on what? Output, and it gives you the next output. Output, right. The input here is 2 and 3. Here's the output, 12 times 1.28 times 1.28. If you multiply it by another 1.28, you get the next output. You get the next output. Okay? So this is growth factor, okay? And here's a decay factor, 0.93. Super important. Okay, so what questions from the worksheet? Let's go over questions from, you have the worksheet that you had to do finish for today. Any requests? How about these? Number 3, the tables. We kind of did these at the end of class last time, right? So how about the graphs?
Let's go with number 5.
He's requesting number 5. She likes it. Let's do number 5. So, if I've got these ordered pairs of input and output and I want to figure out what the growth or decay factor is, it's a decreasing function, right? What am I going to look at to figure out decay factor? Inputs, outputs, one of each. He wants to look at outputs to figure out what the decay factor is. Yep, outputs. So here we're at 1, and what's the output? 30. Here we're at 2. Oh, that's convenient because we know it's that the decay factor corresponds to an increase of 1 of the input. If we increase by something other than 1, we've got a harder task on our hands. But as long as that increase is 1 of the input, then we're home free, because what number are we looking for? The number that if multiplied by the previous output will give us the new output. Okay? So the generic name for this growth or decay factor is B. So since we're going forward 1 in input, we're looking for the number B such that 30 times B is 12. You see, that's how the decay or growth factor works. It gives you the next output. The next output. So if this is the previous output, then multiply it by the decay factor, you get the next output. So what is B? Okay, 12 thirtieths. 12 thirtieths. Or 0.4? Now check it. So this is, now what's this? This is the at 3, so therefore 12 times 0.4 better give us what? 4.8, does it? It does. Therefore we got it. Okay, so our general form for exponential function is a b to the x. We're halfway home. What do we have? B is 0.4, repeated multiplier. So all that's left is a. And what is a? I mean, what does it represent? The value you would get if x were 0, not 1, 0. Okay, starting value is when x is 0. Okay, so here we are, we're at 130, and what we need is what it would be if it was 0. So let's call it a. So set up a statement of a and 30 and 0.4 that makes sense. So what mathematical statement using a? So here. So if it goes 0a and then 130, and we know the decay factor is 0.4, set up a mathematical statement of a and 30 and 0.4. What mathematical statement must be true of a and 30 and 0.4? Okay, that'll work. But so let's think about starting at a. If we started at a, what would we do to a to get 30? Yeah, we multiply by 0.4. So what you said is right. You see? Starting value at 0 times the decay factor will give us the next output 1 unit later. So 30 divided by 0.4, what is that? 75. Okay, does anybody have a question on how I did that? How I thought about that? Whenever the input increases by 1, the output gets multiplied by the growth or decay factor. That's the key. Whenever the input increases by 1, so if we started at A, we want to get to 30, which is 1 unit later, we need to multiply by the decay factor of 0.4.
So that's to find anything behind in the previous
So yeah, it was an unknown. So it was an unknown. So I just took that unknown and said, I'm still going forward, just from the unknown now. I know that I take that unknown and multiply it by the decay factor, I ought to get the next one, which I know. So A was 30 divided by 0.4. Other questions? It's still, see, I'm still showing you that it's always multiplication. It's just to solve for that, then you use division. But still, it's multiplication of the decay factor to get the next output. You see? But right, then to solve for A, it will be division. Did they ask you for anything else besides finding the function? Or that was it? Okay. Oh, percent change. Awesome. All right, so we got 0.4 for the decay factor. Percent change, 40%, right? No, decay is a little trickier, right? What is the percent change? So 0.4 is how much we keep. So what do we lose? 1 minus 0.4 is 0.6, which is 60%. So we're decreasing, by multiplying by 0.4 each time, we keep keeping 0.4, so we're losing 0.6 or losing 60%. What else was, other questions on this? Initial value, function, decay factor. We got it all. Decay factor 0.4, initial value 75, percent decrease 60. Yes, ma'am? So the growth factor is easier because it'll always be 1 point something or something greater than 1. So like what did you get a growth factor for this? For this one? What was it? 1 point what? 1.6. All right, so we're always multiplying by 1.6, meaning we keep what we had before and we increase by what percent? This is a percent increase of 60% increase every unit. Did that answer it? Okay. Other questions on the worksheet? Okay. So I have kind of a good exercise I made up myself here. What I want you to do is, if I can find it. There we go. So, you got some blank space around there? So here's a teacher's salary. 30,000 starting. 3 years later, their salary is 33,165.22. That's the information that we have. How is the teacher's salary increasing? How is it increasing? You're shaking your head. Why are you shaking your head? It's been what? He's saying it can't be determined. What are some possibilities? How could it be grown? What's that? Okay, it is growing every year by somehow. All right, so every year it is doing something, and then after 3 years, it gets to this amount. So the question is, how? Yeah. You don't think it's right?
No, I mean what I was thinking was right.
Oh, okay.
Like you find what the percent is from 30 to 33 or whatever, and then divide that by 3 to figure out the percentage here. But
Okay. So we've seen 2 different ways that it could possibly be growing. What are the 2 different ways that it could be increasing?
Linear or exponential.
Linear or exponential? What would linear growth look like?
Same number.
How would it be growing every year if it were linear growth?
Be adding.
So, right, so everything you're saying is correct. So I'm saying constantly. So the operation would be
Addition.
subtracting. So we would add some amount, and then the next year, what would we do? Add the same amount. And then the next year, add the same amount. Is it possible her salary is growing that way?
Yes.
It's possible. Okay, what would it be if it were exponential growth?
Multiplication.
How would we get the growth in the first year? Multiply by, we'll call it B. And then how would we get the second year? Multiply that by B. And then, all right, so I want you to model it both ways. Can you figure out both ways? What would it look like? So unfold the situation if it's linear growth, additive growth, or if it's exponential growth. So unfold it both ways and give me something that represents both. Go, you can work together.
Next.
So for linear, how can we set something up that makes sense? We could say 30,000. And what would we do? But we don't know what that is right yet. So how we could call it K, right? So you're going to add what? Just K? And then do we know what that is? If we add K? We know what it'll be if we add 3K, right? Yeah, 3 times. Then we know what we'll get. We'll get 33, 165, 22. So we can write that easier, 30K plus, oh, that's kind of bad choice there. So how about G? Plus 3 times K equals this. And so what'd you get for that? 70 cents? 0.07. So, is it possible? Is it possible that this is what our salary's going up? Sure. So if you add that 3 times to 30,000, we're off by a penny, right? Is it off by 1 penny? Okay, so we can overlook that. It's okay. All right. How would we set something up that would reflect that she's getting a percent raise? A percent raise. What would we set up? What would we say? 30,000. I heard times. B. That's it? B to the third, or B times B times B. 30,000 B to the third. And what will that equal? 33. 165. So can we solve for B? Anybody get a value for B? Is it going to be greater than 1 or less than 1? It better be greater than 1, right? Salary is increasing. 1.0. What? What'd you get? 1.03? One more decimal place. 1.034. Someone else get that? Thank you. Okay? So in the case of exponential growth of her salary, by what percent is it increasing every year? What's the percent increase? 3.4% increase. Okay? Any questions on that? So now, tell me which one it is.
Tell you which one it is.
Yeah? I'm giving more info.
We have 6.
Oh, we have 6.
Yeah.
It's exponential.
You think it's exponential? She's finding it's exponential. Yep? Is that what you got to? Exponential. Cool. All right. So write the linear function. If it happened to be linear based on the first 3, it's not, but we can still, just based on those 3 years, we can write a linear function. And then write the exponential function. Write them both. So if the input is the number of years, how can we have a function that will give you the salary after that number of years? So find the function. 30,000? How would you get for linear? It's based on what?
Addition.
Addition, so we're going to add.
1,055.7 multiplied by x.
He wants 1,055.07 times linear function, rate of change. Every increase of 1 year means you add that much more. Additive, linear is additive increase. Additive increase by the amount of the rate of change, right, per unit. All right, exponential. Somebody else. How about in the back 2 rows? Did you get the exponential function?
30,000 times 1.034
What do we think? That's it. So every year in this case, what do we do every year to get the next year's salary? Multiply by 1.034. Notice, so teacher's salary, output or input? It's output. And we keep taking the last salary and multiplying it by B to get the next salary. Output, 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 output. The growth factor is the multiplier on the output to get the next output. Any questions on this? So we know that linear is not correct based on the information from year 6, but still good practice to find it. But according to all 6 years, exponential is right. Questions on that? Okay, so now continue, reorient yourselves to that worksheet on page 145. And start working on that. Question? What is this? No, so that's not right. Oh, this is different. Increases by 2.3% each month. That's not right. So what's the growth factor? It's the multiplier that would give you an increase of 1 point. It would give you an increase of 2.3%. Not quite. That'd be 23%. 1.023. You want to keep what you had before. What you had, just all it did was hold on to 2.3% of it. But it's increased, so you keep what you had before. That's the 1. And then you increase by that much. Yeah. Percent change is 2.3%. That's right. That makes sense? How many times you're going to multiply by that? So is it 50 at 0? Is that right? No. Number of times is large. Sorry. So every 7 minutes, what happens to the population? Doubles. Every 7 minutes, it doubles. So conveniently, we just make n how many 7-minute intervals there are. So every time an n advances by 1, what do we multiply the population by? So this is n advancing by 1. So this is, if we put n over here, it'd be 0. This would be 1, 2. So n is advancing by, every time n advances by 1, what happens to the population?
Doubles.
Doubles. So what's the growth factor? 2. It's a 7-minute growth factor. The 7-minute growth factor is 2. So initial value? 50. And how do we double every 7 minutes? If n is every 7 minutes. 2 to the n. Questions on that? Does that everyone make sense? Okay. So now we want to say, what happens every minute? What happens every minute? So what we want to do is, oh, there it is. Where's the next? I want the next chart. Give me the next chart. I want that. That's what I want. Okay. So look, it was 50 here, and when did it reach 100? Here. So this was before, this was our second line in the table. We know that it doubled. This is times 2. Okay? So the question is then, every minute, if it's growing exponentially, does it grow linearly in between, or does it grow exponentially in between? Yeah, so no matter, if you have exponential growth, no matter how much you cut down your interval, you're still going to get exponential growth. So that means that there's some value, call it A, that we could multiply by what we had 1 minute and would give us what we had the next minute. So, how many times would we have to multiply 50 by A to get to 100? So if I multiply 50 by whatever this is now the A is the 1 minute growth factor. 2 was the 7 minute growth factor. A is the 1 minute growth factor. Meaning, if I multiply 50 by A, I'm going to get this intermediate amount on the way to 100. And then if I take that and multiply it by A again, I'll get the new amount after 2 minutes. So how can I relate the numbers 50 and 100 by A? How can I relate 50 and 100 by the value A? The 1 minute growth factor, in order to try to find it.
2 to the however many minutes over 7?
You want to do 2 to the something?
Yes.
But what are we doing with the 50? We're taking 50 and we're doing what? We multiply by A, right?
Yeah.
And then how many times do we multiply by A to get to 100?
7.
So how can I represent that? 50 times? Yeah, how do I write times 7 A's? A to the 7th, you see? It's not 7 times A. It's multiply by A 7 times, and that will get me to 100. You see? So 50 times A times A times A times A 7 times gets me to 100. So if we start solving for A, look what happens. A to the 7th equals what? 2. Well, look. So 2 was the number we multiplied 50 by to get 100, the 7 minute growth factor, and that's equivalent to multiplying by A 7 times. Just make perfect sense. So multiplying 50 by 2 to jump ahead 7 minutes would be equivalent to multiplying by A 7 times, because that gets A takes me forward 1 minute. So then therefore, what is this number A? So to get A by itself, I got to take the 7th root of both sides, which is the same as 2 to the 1/7. So the 1 minute growth, so find what that is. Find the 1 minute growth factor. What is it? 1 point what? I'm going to put it in red. 1.104. Okay, now watch this. What's the percent increase every minute? What's the percent increase every minute? %10.4%, right? What's the percent increase? So therefore, every 7 minutes, the percent increase is 7 times that much? What was our 7 minute growth factor? I'll make that black. 7 minute growth factor was 2. What's the percent increase for 2? That's 100. That's 1 plus, we keep what we had before, plus we add another 1, which is 100% increase. So this is a really important thing. It's increasing 10.4% every minute, but over 7 minutes, what percent increase does it go up by? 100%. You see this? So every minute, every 7 minutes. Why is that? Why isn't it just 7 times this percent to get that percent? Talk to the person next to you. So this is really important. Why don't you just take the percent increase every minute, multiply it by 7? Shouldn't that give you the percent increase every 7 minutes? It's not, right? It's not 70 point something. It's 100. So talk that over with the person next to you. Why is that? Anybody think how about this corner over here? Got a good explanation for this? It increases about 10% every minute. How is it that it increases then 100% every 7 minutes? Yeah.
Because every time you're increasing the 10%, you're increasing the 10% of the new value.
Yeah.
It's making up for the amount, adding up 7% of that.
You hear what he said? You take 10% of the first amount and you increase it that much. Then to increase it the next time, do we take 10% of the original amount or of the new amount? New amount. So that 10% of the new amount is, how does it compare to the first 10% that we added? Bigger. Every time we add 10% of the previous amount, we actually add a greater amount. So we keep taking 10% of a larger and larger amount. That's why the overall increase then is much more than 70% over 7 minutes. Does anyone know what that principle is called? It has to do with money. There's a principle of money that's the same way. Yeah, what kind of interest? Say it. Compounding. This is the idea of compounding. That you keep taking the same percentage of a greater amount. You're going to keep adding a greater amount. Okay? So that's why 10.4% every minute is equivalent to 100% every 7 minutes. So let's write the function now. What did they call? Did they call this x? Okay, so if every minute is x, we said every 7 minutes was n. I'm going to start over here. So we had f of n, right? Is that what we said? F of n was what? 50 times every 7 minutes, it doubles. Growth factor 2. All right, so now if we did f of x, where x is every minute, what did we find that the growth factor was? So exactly, what was it exactly? It was 2 to the 1/7 to the x. That's a 7. And that number 2 to the 1/7 we found was 1.104. So that's approximation. 2 to the 1/7 is exact. So these are both the same. They represent the same growth. N is the number of 7-minute periods, and x is the number of 1-minute periods. Okay, what's next in that worksheet? Is that an example? All right, start at number 3. See how number 3 goes. Work on number 3, which is on page, what page is that?
147.
147, number 3. We can just do parts A and B, we'll be good. So in terms of 4-minute intervals, what do we got? A represents initial value. How much? 210. So now just the question is, this is a 4-minute period, every 4 minutes, what is the multiplier? What is the multiplier for every 4 minutes? 1/3? 1/3 or 2/3? It loses 1/3, and the multiplier is always what we keep, right? So that's about the decrease. So remember with decay, the multiplier is about what you keep, keeping 2/3. Okay? We start with the same amount every minute, but following the pattern from before, what would we multiply by every minute to get the next new amount? So say it. 2/3 to the 1/4. 2/3 to the 1/4 is now the new multiplier. Oh, so let's just say t. Sorry, that's bt up there. Okay. Get started on your homework this weekend.